Yeah.
All right, so a very warm welcome to all of you. So what we are doing is to essentially organize the second RL workshop this year, and we are very thankful to a very generous grant from Walmart. So we wish to thank the Walmart Center for Tech Excellence at IISc for supporting this workshop. And today is going to be a tutorial session. It will have two parts. First part will be the theory part of it, and then the second part, which will be in the afternoon, will be the applications. For maybe that will mostly be driven by programming based sort of. You will get to know once you are in the afternoon session. That will be conducted largely by our PhD students. So for the morning session, we are very honored to have Professor M. Vidyasagar from IIT Hyderabad. Professor Vidyasagar has had a very long journey. He is the most well-known face in India in the field of controls. He started his career as in nonlinear control theory. He has made extremely significant contributions. And he did his bachelor's, master's, PhD from the University of Wisconsin at Madison. And subsequently, for nearly 20 years, he was a professor in Canadian universities. When he came to India, he was heading the CARE, the Center for Artificial Intelligence and Robotics at DRDO. And then he joined TCS Research, where he was an executive vice president. Subsequently, he went to the University of Texas at Dallas again as a chaired professor, and now he is at IIT Hyderabad. He has had he's had many notable contributions and is very well known. Extremely, he has received many awards and honors. The most prominent of them being he is a fellow of the Royal Society, London, and he is currently the SERP National Science Chair at IIT Hyderabad.
Okay, sir. Yeah.
We are very fortunate to have you, Professor Vidyasagar. It's all yours.
Thank you. Yes, thank you very much. So I asked the organizer. No, I don't think that will give an echo if I have this thing. Okay, just put that thing down. So, can everybody hear me all right in the back? Yeah, okay. So I asked because you have a 3-day workshop following with several advanced talks. Professor Bhatnagar and Professor Tope asked me to prepare the students to appreciate some of those talks. So I said, okay, what do you want me to talk about? They sent me what I can only describe as, with due respect, a very ambitious curriculum. And I had 3 hours in which to do it, and 3 hours is not quite enough. So let me see. Yeah, so I'll do the best I can. The title theory session 1, 2, and 3 roughly correspond to the breaks, but we are starting very late. We're starting at 9 o'clock. We're supposed to start at 9 o'clock, and we're starting at 9:15. So, shall are the break times very rigid, or we just stop when at a reasonable time? Okay, so whenever I think there's a logical point, I'll stop. So there's a break. And then after that, at sessions 2 and 3. How are you? Okay. Miss Piyushi Manipriya has taken this whole course in IIT Hyderabad. I don't know why she has come for my tutorial, kind of a waste of time. But anyway, it's all right. Let's see. All right. So, I taught this course in the first semester of the current academic year, starting in August and ending in September. And this course had a fairly elaborate title. It is called Stochastic Algorithms for Non-Convex Optimization and Reinforcement Learning. So it was a kind of an omnibus course. It had 2 very different themes. One was non-convex optimization. The other one was reinforcement learning. But the common thread was something called stochastic approximation. So you can go and look at this URL, and if you don't have the ability to write it all down, it's quite easy. Just look for my IIT Hyderabad website, look under teaching, and you can navigate to this page. I have put the entire slides for the course online, and the relevant modules that I'm going to try and cover here are 5A, 5B, 5C, and 6. The first 4 modules are, in fact, the non-convex optimization part. But you can read those too if you're interested. And the course notes, as they are at the end of last semester, they're also available online. You're welcome to download those. One of these days, this will become a book published by Springer. But lots of new research is happening in the stochastic algorithms. So that's part of the reason why the book is getting delayed. So there are some nice references in this area. Kind of the classic book that everybody refers to is by Sutton and Bartow. It's called Reinforcement Learning. The first edition was in 1998. Second edition is now. And the second is by Dmitry Butchek, not Carr. And it's called Reinforcement Learning and Optimal Control from 2019. And more recent book by Sean Mine called Control Systems and Reinforcement Learning. It's from 2022. So the point in these 2 books is that if you come from a control theory background, these last 2 books treat reinforcement learning and control systems, optimal control specifically, side by side. Whereas the Sutton and Bartow book is a much more traditional machine learning type of a book. Doesn't really mention too much about controls. Okay. So here is a summary of today's lecture, the first lecture. A quick overview of reinforcement learning, and where does reinforcement learning fit into the overall concept of machine learning. Because today, if I were to ask all of you young people, what comes to your mind when I say machine learning or AI, they always think ChatGPT. Well, I want you to know there's a lot more to machine learning and AI than ChatGPT. But reinforcement learning is only a part of that. And the paradigm that people use is known as Markov decision processes. And I'll just describe what those are. Then once you formulate the problem, how do you solve the problem? And I'll talk about 2 techniques, and that's the outline. So let's start with what's reinforcement learning. So like many phrases in technology, there is no precise meaning or a precise definition for this phrase. There's sort of a vague understanding. And frankly speaking, in my view, it's a little bit counterproductive to try and define these things too rigidly. It's more a philosophical thing. So my 1-sentence summary is that reinforcement learning is the study of sequential decision making under uncertainty. Okay. Now all these phrases are essential. So in reinforcement learning, there is a person called the learner or the agent. Now, of course, nowadays, the learner can also be another computer program, but initially it was a human being. And the decisions taken by the learner are usually called actions. Now, the decision making has to be sequential. In other words, it's not just a one-time decision, but you take a decision, see what happens, based on that you take the next decision, and so forth. So that's one of the characteristics of reinforcement learning, that sequential decision. Third bullet is that you are taking all these decisions with incomplete information. Imagine trying to play a game, but you don't know the rules of the game. Okay. When you play a common game like chess or bridge, you know the rules of the game. You might not be very good at it, but at least you know what will happen when you do something. But suppose you're playing a game and you don't know what the rules are. For example, suppose you're trying to navigate a car in an uncertain terrain. That's an example of incomplete information. So when you take an action, the consequences of your action are determined by the external environment, which you don't know. And the last point is, I think, somehow the least emphasized in reinforcement learning. The fourth bullet says that the environment will affect the consequences of your action, but it is also true that your action will affect the environment as well. Okay? So, by the way, don't take so many photos. I'm going to give the slides to the organizers. Please listen. That's more important than taking photos. Okay? Yeah, I'll mail all the slides to you. You can put them up on your website. So this last bullet, that the actions affect the environment, which in turn affects the next action, and so forth. This is kind of characteristic of reinforcement learning. Now, when you make decision making under uncertainty, ideally, the uncertainty should decrease as time goes on, because imagine, as I said, the example of a game where you don't know the rules, but as you keep playing, you should get some idea what the rules are, even if it's not perfect. And the second bullet on this slide is probably the single most important idea in reinforcement learning. It is something called a policy. So what you observe about the system is often called a state, and action is what you take. And based on your observation, which is the state, what is the action you take, that is called the policy. Now, the policy ideally should not be static, because the policy should depend on the environment, but you don't know the environment. So as you learn the environment, you keep adjusting the policy, right? So the next bullet says, well, all right, how do you know if your policy is any good or not? And typically, the whole thing is stochastic. Therefore, whatever measure you have is only some expected value of something. It's not going to be one number that you can measure, but the expected value of some random variable. And the goal of learning, of course, is that eventually your learning algorithm should come out with a good policy. Ideally, you should come out with an optimal policy, meaning the best possible policy amongst all. But typically, this is not possible. Also, when you go at the theoretical side, all these things are, the proofs are asymptotic, which basically means that as time goes to infinity, you come up with the optimal policy, but infinity is a long time to wait. So you usually chop off the problem at some point and hope that what you have till then is a good policy. So there are three ingredients in a typical RL problem. One is called the state, which is basically the environment encapsulated form. The action, which is what you take. And the third one is the reward. It's the function of both the state and the action. So you take an action, the environment gives you some, some reward. And then as you keep taking more actions, you keep getting more and more rewards, and you accumulate all of them. So to keep life simple, we'll assume that there is some finite set denoted by calligraphic x, and the state at time t is denoted by x of t, and the state space x is a finite set consisting of elements x1 through xn. Now, I hope you're all good at spotting fonts, because the state space is the calligraphic x, the state at time t is the uppercase x, and the elements of the state space are lowercase symbols, right? So there is a menu of actions available to the agent at each state and at each time. So the set of actions is also assumed to be finite, and I'll denote this by u1 through um. N need not be the same as m, meaning the number of actions need not be the same as the number of states. And invariably, in a typical reinforcement learning problem, the number of actions is very small. 2, 3, 5, 10. These are all very typical numbers. On the other hand, n, which is the number of states, can be enormous. For example, if you play a game called blackjack, small n, the number of states, is supposed to be of the order of 2 to the power of 100. Okay. So that disparity between the number of states and the number of actions is one of the governing factors in how you design good learning algorithms. If the number of states was comparable to the number of actions, you would do the algorithms in one way. But since there are so many more states than actions, you have to tailor your design accordingly. Now, the assumption, the second sub-bullet, is that the set of actions available is the same at each state. This is not always true. So think about terrain navigation problem. So you can think about a very simplified model. If it is planar, you have basically 5 actions. Don't go anywhere, stay. Go forward, go backward, turn left, turn right. But if you're right against the wall of the state space, then you can't turn right because you will hit the wall, like that. But it doesn't really restrict the problem very much to assume that at every state you have the same set of actions. And the theory can be easily modified to the case where this is not true. Now, everything is assumed to be a random variable. So x of t is a random variable, assuming values in this finite set x. And the statistics of the next state are defined by the current state, xt, and the current action, ut. And the third ingredient I mentioned was the reward. So the reward is a function of the current state and the current action. It's a real number. Now, x and u can be abstract variables. It's not necessary for x and u to be real numbers. In fact, they're not real numbers often. In the example that I gave of autonomous navigation, so stay, go forward, go backward, turn left, turn right, that's the set of actions, and that's an unordered set. I mean, there is no natural ordering between these 5 actions. The minute you say real numbers, there is an implied ordering that often messes up your understanding of the problem. Same thing with the states as well. But the rewards have to be a real number. For example, if you turn right and hit the wall, then you get a very negative, large negative reward because you've crashed the car, right? And I generally prefer to assume that the reward is given at the present time t. Some authors assume that the reward comes at the next time. Now the next question is the reward itself random? In other words, the state can be a random number, but once you make an observation, the state is known now. And the action is definitely known because you are the one taking the action, so there's nothing uncertain about that. But given x of t and given u of t, is the reward also random? Well, you can make it random if you feel like, but to avoid technicalities, you have to assume that if it is a random reward, it is in some compact set. And the point about taking a compact set is that the random reward has finite movements of all orders. Okay. But most of the time, people also just assume R itself is a discrete valued random variable or completely deterministic. So these are all the approximations. And then this is the last point about reinforcement learning. There is something called the discount factor, which basically means that a certain reward given now is worth much more to you than the same reward that's given sometime later. So this gamma tells you the factor by which a future rewards are discounted. So 100 rupees today is worth 100 gamma next time, 100 gamma squared, 2 time steps later, and so on. That's one class of learning problems. The other class of learning problems is where you don't care about discounting. You are happy with the money no matter when it comes. In this case, it turns out that the mathematics is a little bit different, and you cannot just simply keep adding up the rewards because that will go to infinity. So instead you look at the average of the future rewards. And this formulation is not discussed in this module. When we go to module 3, I will discuss it. So please feel free to ask me questions at any time, all right? If you don't understand something. So because the reward depends on both X and U, the same action taken at a different time need not produce the same reward. Okay? And a lot of times this dependence of how xt plus 1 depends on ut is not always known. And the fact that this dependence is not known and has to be learned, that is sort of the core of what differentiates reinforcement learning from traditional optimal control problems where you assume that you know the system to be controlled. Okay, so this bifurcation kind of took place in the 1960s, long time ago. So there are a few well-known applications: autonomous navigation in an uncertain environment, game playing typified by AlphaGo, AlphaZero, and AlphaFold, and you know that AlphaFold was just awarded the Nobel Prize in Chemistry.
Sir,
Yes, sir.
one question.
Yeah.
Sir, like
Previous slide.
yeah, previous slide. Sir, we are saying that reward will be a random function. I'm not able to understand. Like if we are
No, reward is either a known function given x and u, or it is a random function of x and u. Okay, if you don't assume a random reward, if you reward. But the theory doesn't really become a whole lot more complicated if you assume that it is a random function as well.
okay. And sir, one last question from my side. You told that action can change the environment.
Pardon me?
The action which we are taking, it has the ability to change the environment. Like typically we assume that environment is if like action is not going to change it. So that can you tell an example so that
No, but that's what I meant, that one of the defining features of reinforcement learning is this two-way interaction between the environment and the action on the environment.
So like I was thinking that whatever action we are taking, the environment is not going to change.
How do you know that?
Okay. Like that is the assumption that I was thinking.
Well, I'm saying your assumption is not correct. I'm telling you about for the fourth or fifth time, from the whole point of reinforcement learning is that actions affect the environment as well.
Thank you, sir.
Any other questions? Okay. Right. So, yeah, as I mentioned, this last item, AlphaFold, two of the people who proposed that, Demis Hassabis and John Jumper, they shared half of the Nobel Prize in chemistry this year. The other half went for a completely conventional chemist. And I don't know what exactly he did. All right. So, next question I was asked to talk about was, where does reinforcement learn? So, you can broadly classify reinforcement learning into three categories: supervised, unsupervised, and reinforcement. And reinforcement learning sit partway between supervised on one side and unsupervised on the other side. So I just have about 2-3 slides about supervised and unsupervised learning. So in supervised learning, the learner gets immediate feedback and mostly it is accurate. In unsupervised learning, the learner gets no feedback. And in reinforcement learning, the learner gets a partial and delayed feedback, which is sometimes random. So here's a couple of slides on reinforcement learning. Let's see, I have to, my mouse keeps sliding off the this thing because of the slope. So I have to put it somewhere. Okay. Classic supervised learning problem. Right? So you have a training data, and this is labeled. So for example, if you have a pattern classification problem, say you have to figure out, is a particular tumor benign or cancerous? So you have a whole bunch of tumor images. Some are known to be, and you have to classify which is which. First you train your classifier on the basis of the labeled samples. Then you are given a new sample, and you have to get the right answer most of the time. That is an example of a classification problem. When the label is binary, like the tumor is benign or malignant, that is called a classification problem, where the output, the label, is a real number, not just binary. Then that is called a regression problem. So, for example, if you want to predict tomorrow morning's weather, the weather temperature is going to be a real number. And deep neural networks, which are very widely used even in reinforcement learning, are an example of supervised learning. Now, unsupervised learning is at the completely opposite end of the spectrum. There is no information given to you at all. You get a whole bunch of samples, and then you have to detect some pattern in this completely unstructured data. So the statisticians call this problem as clustering. Machine learning people decided to call it unsupervised learning. So the problem is you are given a whole bunch of vectors in some reasonably high dimensional space, and you want to group them together in such a way that each vector is closer to the centroid of its own cluster than to the centroid of all other clusters. So here's an example. So there are 3 clusters here, 4th cluster, 5th cluster, and the stars indicate the centroid. That means the average of all the vectors in that cluster. So the point is that if you take this red, it is closer to that centroid than it is to any of the other centroids. Okay. And similarly with these blue dots, and similarly these sort of olive green dots, and so forth. Sorry. Now, when you have a new, how do you use this for classification? If you get a new test input, so suppose you get an input there, you figure out to which of the centroids is closest. So if my test input is there, it's closest to the blue centroid, so you assign it to that. If it is here, you assign it to that. If it is here, well, you have a problem because it's roughly equidistant to the olive-colored centroid and to the green centroid, and so forth. But the real problem with this is not that. The real problem is that given a bunch of vectors, to achieve this objective, namely that each vector is closer to the centroid of its own cluster than it is to the centroid of any other cluster, that problem is NP hard. Okay, so most people use a method called k-means, which is a heuristic. It sort of works, and also this problem kind of becomes meaningless if the vectors are extremely high dimensional, because it turns out that clusters tend to collapse. So these are called Cohonan maps, self-organizing maps, etc. The supervised learning standard methods are support vector machine, kernel-based machines, and deep neural network. So that's just a very, very brief introduction. Now let's finally come to Markov decision processes. Now, until now, we've just been waving our hands and not making anything too specific. Now we have to become more precise. So now the environment, you think about it as a Markov process, x0, x1, and so forth. All these x's belong to some finite state space for the sake of simplicity. So here is x of t. You measure x of t, and you plug that into what is known as the policy, which will generate an action u. So u is a function of pi, is a function pi of the current state x of t, and the current state x and the reward u go into this box, and that produces the current reward r. Okay. Then this action goes and affects the environment by determining the next state xt plus 1 in some random fashion. And that's a Markovian dependence. Okay. Now there are lots of things you can do. For example, if you look at this box, I have put just pi. I have not put pi of t. So I'm assuming that the policy is static. In other words, whenever you see one state, you take the same action. Whether you see it at time 1 or time 100, it doesn't matter. But you can get rid of that assumption. You don't gain very much, as it turns out. So most people stick to this assumption that the policy is static. Okay? Given a state, the corresponding output is always the same. Similarly, the reward, if it is random, you assume, okay. If it is random, you assume that the characteristics of the random process are not changing. The statistics of r as a function of x and u are constant with t. So all these small changes you can make, they don't make the problem more complicated. So how do you go beyond this? So you look at a Markov decision process with unknown dynamics. That is the most popular formalism for reinforcement learning. It's not the only formalism, but that's by far the most popular formalism. So you have to understand what is a Markov decision process. So I'm going to lead up to it in 3 stages. One is called Markov processes, Markov reward processes, and Markov decision processes.
What happens to the reward in the previous line once you get the reward?
Oh, what happens to the reward? Well, depending on what I mentioned earlier, either you keep accumulating the reward with a discount. So at the end of the run, you have a total discounted reward. Or you take if it is not discounted, you just take the average. So whatever you get, either the discounted reward or the average reward, that's a function of this policy. And the idea is to choose the best policy. I'll make this more precise later. Yeah.
So unknown dynamics doesn't mean that the policy is unknown?
No, you choose the policy. You as the learner are choosing the policy. So the policy is definitely known, and you can even adjust the policy from one time to the next. What you may not know is the dynamics of this Markov process.
States and the action.
Yeah.
Okay.
Anybody else? Okay. So let's start with the basic. Yeah, I'm just mentioning. There are 3 stages. One is called Markov processes, Markov reward processes, and Markov decision processes. And I'll go through each of them in turn, okay? So in Markov processes, I think most people know what a Markov process is. But just to refresh your memory, I'll define it again. So suppose you have some finite state space X, which is x1 through xn. And what happened here? Here we go. This is the Markov process. Yeah. So it's a process. What is going on? I missed once. Sorry. Little mouse trouble. I was looking for this slide. So suppose you have a finite set, and x of t is a stochastic process. Now, I'm not going to get into all the technicalities of what a stochastic process is. So let's just assume that it is a sequence of random variables taking values in a finite set. It's absolutely baby problem. So suppose y is some element of the state space, and u is from 0 to time t. It's a t tuple, t plus 1 tuple. And then let x of 0t denote x0 to xt. That should be actually That's the wrong font, I'm sorry. That should actually be this font. So anyway, so it's just the past history of the process. So this process is said to be a Markov process if whenever you take any element in the state space and any past history, it's true that the conditional probability of the next state, given all the past history, is exactly the same as the conditional probability of the next state, given only the most immediately past state. In other words, telling you what the previous states were before time t doesn't make the problem any different. Okay. So essentially, you can think about a Markov process as a process that has a memory of one time step. What happened more than one time step ago doesn't make any difference. Now, obviously, you can generalize this definition to say that a k-step Markov process, but I'll stick to one-step Markov processes. So the dynamics of a Markov process on a finite state are completely characterized by what is called the state transition matrix. Okay? And I'm going to denote it by A of t. So A of t is the conditional probability that at time t plus 1 the state is xj, given that the current state is xi. Xi and xj are the elements of the state space, right? Now, when I write A of ij, in my notation, I is the current state and j is the next state. Some authors do it the other way. So if you're going to read books, make sure you check what is the notation that the author is using. All right. And I also put the time probability doesn't depend on t. For every pair of states xi and xj, then the Markov process is said to be stationary, in which case there is just one n by n matrix where n is the number of states that characterizes this stationary Markov process. Okay? I'm sure you've all seen this before. Now let's talk about just a little housekeeping, excuse me. Yeah. So let's talk about what is known as a Markov reward process. So you have a Markov process X. This slope is introducing some very complicated dynamics, which I have to deal with. Okay. So if you have a Markov process on some finite state space with transition matrix A, and suppose there's a reward function, which for the sake of argument can be random also, and it maps the state space into the real numbers as well as the discount factor R. So you define the expected discounted future reward V of xi to be the expected value of this discounted sum. So suppose you start in initial state xi. So x at time 0 is small xi. Depending on the dynamics of the Markov process, this defines xt, x1, x2, and so forth in a random fashion. And each of those states gets a reward, which itself could be random because of two things. One is x of t is random, so R of xc is random. But even once x of t is fixed, R itself could be random on top of that. It doesn't really make any difference. And then you just keep summing up these rewards with a discount factor. And remember what I said, that if R is a random reward, you assume that it takes values only in some compact set. So and because gamma is less than 1, this summation is going to be well defined. Okay? It could be random, but it's certainly well defined. So then you take the expected value, and that is called the expected discounted future reward. So let's look at all these words. Y future because it's going all the way from 0 to infinity. Y discounted because of this gamma, and Y expected because you're taking the expected value of this random sum. Now, because everything is nicely absolutely summable, if instead of first summing and then taking the expectation, If I take the expected value at each time t and then add them up, you get the same answer, right? Okay, now the first question is, how can you compute v of xi for each xi? Now remember that the value, this thing here, does depend on the initial state. If you start the Markov process in a different initial state, you will get a different number in general. So how do you do that? What happened here? I seem to be hitting the wrong buttons all the time. Ah, there we go. Sorry, little bit of randomness in my clicking the buttons, it looks like. Okay, so you have to cope with that randomness on top of all the other sources of randomness I mentioned. Okay, so let me just remind you what the problem is. How can we compute the value v of xi for each state? So you write down an n-dimensional vector, which is the value corresponding to the first state up to the last state, and then the rewards corresponding to the first state and the last state. If the reward is random, then this is just the expected value of that random reward. Anyway, these are both deterministic real vectors of dimension n, and the key point is that this value vector satisfies the simple linear recursion. Okay. Now, why does this equation have a unique solution? Well, A is a state transition matrix, so it's pretty easy to show that its spectral radius is 1 and gamma is less than 1. So the spectral radius of this matrix gamma times A is gamma, which is less than 1. So you can move this to the other side and you can write V is equal to I minus gamma A inverse into V. That's a well-defined formula. But if n is a huge number, which it often is, trying to do this matrix inversion is not a very sensible thing to do, right? So that's about all I'll take about the reward processes. Now let me talk about the decision processes. So the difference between a Markov reward process and a Markov decision process is, in a Markov reward process, x of t determines the conditional probabilities of x of t plus 1. In a Markov decision process, of the state space, there are additional action variables which take values in a finite set U. So if there are m different actions, there are m different state transition matrices, not just one. So you look at this quantity, the conditional probability of xt plus 1 equaling xj, given that the current state is xi and the action is uk. So you denote that as aij subscript and then uk as the superscript. So for a fixed action, this A is an element of a transition matrix. So basically what you have are m different state transition matrices where m is the number of actions. And the reward now depends not just on the current state but also on the current state and action. And again, you can make the reward to be random. I don't discuss this possibility too much. I just assume a deterministic reward. Okay. So now what takes the place of the reward, the discounted future reward? Not much difference really. But the key idea is that of a policy, that is a way of assigning actions to states. In other words, if the current state is x of t, you substitute into this map pi, that gives you an element in the set u of action, and you call that u of t. So a deterministic policy is one where this map is a fixed map. There's nothing random about it. So the set of deterministic policies has finite cardinality. Since for each state you can take one of this many actions and there are that many states, the number of possible deterministic policies is this finite number. Now the fact that this is a finite number is actually a very small consolation, in the sense that if you have two actions, which is theoretical minimum, because if there's only one action, then there's nothing for you to do, right? So 2 is the theoretically minimum possible number of actions, and you have 100 states. This is already 2 to the power of 100, which is about 10 to the power of 30. So there's no way in which you can enumerate all the policies except in really toy problems. But it turns out, as you will see in topics 2 and 3, that there are many situations in which it does not work to use a deterministic policy. You have to use a so-called probabilistic policy, which means this pi doesn't map states into actions, it maps states into the set of probability distributions on U. Now U is a finite set, so probability distribution is just a non-negative vector whose components add up to 1. But the point is that the set of probabilistic policies is uncountable. Some authors make a big deal about the fact that in deterministic you have a finite set of actions, and in probabilistic you have an uncountably many policies. 1 minute. But the difference is essentially none, because as I mentioned, this can be a huge number. Yeah?
So should this be x to the power u instead?
No.
No?
No. That's a very common mistake. Think about it.
Okay.
There are x elements, and each of them can have u possible values.
So I have a question. So how to understand the difference between the transition matrix and the policy?
No, there isn't any commonality between them. So once you take a particular action, you have the corresponding state transition matrix. If you take a policy, at each time you have a different policy, which means that even if you hit the same state at a future time, you will still get the same action if it is a deterministic policy. And if it is a random policy, then you have possibly a different action even when you hit the same state. However, even if you have a deterministic policy, so you hit the same state action pair, if you hit the same state, you get the same action, but the next state doesn't have to be the same as it was last time because of the randomness of the Markov process. The statistics of the next state are determined by that state transition matrix. So there are many, many layers of randomness. The simplest layer of randomness is that current state does not uniquely determine the next state. If you take a deterministic policy, current state uniquely determines the next action. So if you hit the same state at some future time, you'll take the same action. But the next state, the second time, need not be the same as the next state the first time, because that's a random transition. Now if you have a probabilistic policy, even when you hit the same state, you won't necessarily take the same action. So that introduces one more layer of randomness into the dynamic. Okay. Now I'm just going to go to this slide. I think it will answer a lot of your questions. This top sentence in the slide, maybe I should have put it in the previous slide, but I put it here. The key observation is whether you use a deterministic policy or a probabilistic policy, the resulting sequences of x's is always a Markov process. This is not that obvious, but you have to think about it, but it is true. So for example, suppose you have a deterministic policy. So the corresponding state transition matrix, I'm going to denote it by A of pi. The ijth element of that state transition matrix is the ijth element of the pi of x by matrix. So if you want to download my notes from my course website, you will see a simple derivation of this formula. It's not very hard, but still, it does look a bit mysterious at first glance. And the reward function, this is easy to see. For a corresponding to a policy pi, the reward at state xi is r of xi pi of xi, because xi is the state and the action is always going to be pi of xi. So you substitute that, this is the reward associated with the policy. Now, if you have a probabilistic policy, you don't have a simple formula like this. You actually have an expected value of the state transition matrices depending on the policy pi. I decided not to show it because I don't have enough time, but this point is certainly correct. Whether you have a deterministic policy or a random policy, the resulting sequence of x's is a Markov process. And more interestingly, this is not relevant for topic 1, but for topic 3, when we get there eventually, you will see that not only is x a Markov process, but the joint process x and u is also a Markov process. We use that to design optimal policies. You won't see that for an hour or so at least. Okay. So what are the core problems? And I'll cover these core problems and then we can take a break. Suppose you have a Markov decision problem with known dynamics. So that means you know all these matrices. Okay? You know all those matrices. What you would like to do is find an optimal policy, which I'll call pi star, such that, okay, let me just mention one more thing. Because I have a known reward and a known state transition matrix, I also have a known discounted future reward. And that is what I'm denoting by V. So once you fix a policy, for each state there's a corresponding discounted future reward, which I'm going to call as V, as defined earlier. So the question one can ask is there an optimal policy, pi star, such that for each state, the value of that policy is the maximum possible value over all possible policies? Can you determine this? That is a problem of finding the best possible policy, if you know the dynamics. Now, there are lots of hidden assumptions here, and these bullets list some of those. First of all, I'm saying that there's a pi star for one policy such that this maximum relationship holds for each state. So you can ask, is there one policy that is optimal for every state? Why should it be? Maybe for different initial states, different policies are optimal. Well, it turns out no. Actually, there is one optimal policy for all the states. Well, does an optimal policy always exist? Yes, it does. And is the optimal policy unique? Not in general. But more interesting is that if I replace pi of d by pi of d, pi of p by pi of d, meaning I don't allow probabilistic policy. I restrict myself to only deterministic policies. For each state, I am allowed to choose only one action. Is the maximum reduced? I mean, in theory, it could be, because I'm restricting the choices you have. And one of the more interesting things is, no, you don't lose anything. The best value you can get over all possible probabilistic policies is not any higher than the best value you can get over only deterministic policies. Okay? So let me think about let's think about the methods of solution. Okay. Here I just said does an optimal policy exist? Yes, but knowing that it exists is not the same as actually finding it, right? So that's the point of this module, methods of solution. So there is this thing called the Bellman equation. So let me define V of pi star to be the maximum possible over all possible policies for each initial state. This is an n-dimensional vector where n is the number of states. It satisfies this recursive relationship, which is known as the Bellman equation. What it says is, for a state x sub I, V star at x sub I is the maximum over all possible actions of this quantity, R of xi uk plus gamma summation over a ij uk V star of xj. Now this is a recursive relationship because the unknown quantity V star is occurring on both sides, right? So the proof is surprisingly messy, but here's an easy way of rationalizing it, which is not a proof. So suppose that somehow you know what to do from time 1 onwards. Okay. You have figured out V star for each state starting at time 1. Now suppose at time 0, the state is x sub I. Okay. Now each action A of k, what does that do? Well, if you apply the action uk and the state is x sub I, then the transition matrix is A of uk. So the probability of the next state being xj is given by this. So the expected value at the next state is summation over all possible next states of A sub ij super uk of this quantity. So if you take the best possible decision from time 1 onwards, I can replace this by V star, okay? So that tells you the best possible value from that time 1 onwards. So the maximum value at time 0, what is it? Well, at time 0, you look over all possible actions, think of the immediate reward and the best possible future reward, which is that quantity. However, because the problem is a stationary problem, V star at 0 is the same as V star at 1. So you can this and that are both V star, and then you get this formula. Now this is not a proof. As I said, this is only a rationalization. But why is this statement true? Okay, well, this doesn't help you to solve the problem. It's just a way of thinking about it. So one way of solving for V star is the so-called Bellman iteration. You define a map from n-dimensional vectors to n-dimensional vectors given by this. Take a v-dimensional vector V and take R of x sub I being the ith component, plus summation of gamma times summation over all possible next states A ij uk v sub j, and then take the maximum over all u's. Now you may get a bit lost in the notation, but basically this is just a map from n-dimensional vectors into n-dimensional vectors. You take this n-dimensional vector, substitute it in there, take this maximum, you get another n-dimensional vector. So the fact is that this is the monotone map and its contraction with respect to the L infinity norm, and the contraction constant is gamma, which is the discount factor. So because this is a contraction, okay, I didn't do that. So because this is a contraction map, you can start with any arbitrary initial guess, keep applying it repeatedly, and you will converge to the answer. Contraction mapping theorem tells you that. However, what is the rate at which these iterations converge? Well, the contraction constant is gamma, which is the future discount factor. And typically the future discount factor is very, very close to 1. In the sense that, theoretically it can be anything, but in a realistic problem, if you get a reward at time 1, it's worth less than at time 0, but not a whole lot less. That wouldn't be realistic. So you may say that, well, the discount factor may be 0.99 or 0.98, something like that. It's not half, it's not a quarter. That's not a realistic problem, okay? So that means these iterations converge really, really slowly. So you have to figure out better ways of doing this, and that is the topic of the so-called temporal difference, temporal difference learning. Now, one of the major advances in this area was the introduction of something known as the action value function. And this action value function made life very simple. So here is a definition of the so-called action value function for a fixed policy. And this is a very bizarre looking definition. So you have to say full credit to the people who first thought of it, because it's not very natural way to think about the problem. So what they said was, okay, let's say that I fix a policy, meaning for each state there's a corresponding action. So that's pi, the policy. Can you people see stuff moving on this table? Somehow I keep getting distracted. Anyway, so let us define Q of pi, the action value function Q of pi. It maps the state space times the action space into the set of real numbers. And it is defined as follows. It's the expected value from time 0 to infinity. It's the expected value of the sum from time 0 to infinity of the discounted future rewards starting at the initial state x sub I and the initial action uk. So what this says is, at time 0, you don't follow the policy. You pick the action whatever you feel like. But from time onwards, you choose the policy, pi. U of t equals pi of xt. Now, some authors define this as summation from 1 to infinity as opposed to 0 to infinity. It doesn't make any difference. And do you see why? Because at time 0, x of 0 is x sub I, u of 0 equals uk. So this is just a constant which doesn't depend on anything. So you're just adding some deterministic constant to q. So whether it's there or not, it doesn't really make any difference. So this is, as I said, a very unnatural looking definition. The idea that you have a policy but you don't follow it immediately. But this very non-obvious idea makes life very simple. So Q can be viewed as a real vector of dimension size of state space times size of action space, or an x by u matrix. So depending on the problem formulation, you can think of it as one huge vector or a matrix, and that depends on the situation. Okay? Now, it turns out that the optimal action value function, if you define it by this, means suppose you know the optimal value vector and you define this function. This is just a definition. So this Q star satisfies this recursive relationship. Okay. Now, what is the big deal here? Q star of xi uk is R of xi uk plus this summation where you take the maximum over all second arguments. Compare this with, here you're taking the maximum outside the summation. This is the source of the problem in the Bellman iteration. Here you're taking the maximum inside the summation. So as a result, what you can do is the following. You define the so-called F iteration, and this is at it turns out that this you can think about as a map from either vectors to vectors or matrices to matrices. It turns out to be also a contraction in the L infinity norm with the same constant discount factor as the contraction constant. So these iterations will converge. And one thing I want to say was, once you are given a state X, if you know Q star, the action that achieves this maximum turns out to be the optimal policy. So in other words, once you know Q star, however you get it, finding the optimal policy is nothing more than just reading off what is the maximum overall possible policy. Now at this point you may say, wait a minute, you still have to do this maximization. What are you saving? Well, remember what I told you. The number of actions is usually very small. You may be just comparing 2, 3, 5 elements and seeing which is the biggest. So it's a very easy problem to solve.
What is the difference between Q and V?
There is no difference as such. You can think about defining Q like this, okay? And just like V satisfies its own recurrence equation, namely this one, Q satisfies its own recurrence equation, namely that, okay? So at this stage, it doesn't look like you have achieved anything, because you have just replaced one implicit equation by another implicit equation. But the advantage is, if you can solve this implicit equation, determining the optimal policy is very easy. You just do this maximization, fix the state, maximize over all possible W's. That's the optimal policy for the state X sub j. That's what you achieve. Are you clear? Okay. So now, both the Bellman iteration and F iteration require complete knowledge of the MDP dynamics, right? Just look at it. How do you actually implement this iteration? You need to know these matrices, right? But suppose you don't know those matrices, then how do you solve this problem? And that is the topic of the second part of today's lecture. So I think this is a good place to take a break.
I have a question. So in a Markov decision process, the policy has to be Markov, or it can depend on the whole history?
No, policy is usually assumed to be memoryless. Let me just see if the policy is assumed to be X into U. It's not xt minus 1 all the way back. It's just current state. You can actually say a finite memory, and the problem doesn't become any harder. But what you can't have is this trailing memory that goes all the way back to minus infinity. That problem is very difficult to solve. So implicit in this formulation is that the policy is a memoryless policy, or at best has a fixed memory that you know ahead of time. Any other question? Okay, then we can stop, I think.
Okay, we'll have a break now. We'll meet at 10:45. Tea, coffee, right now.
When I teach these kinds of courses, there's what I call the radioactive half-life decay. Each lecture has half as many students as the previous lecture. I think that on a time scale of 1 hour, that's too short for the half-life phenomenon to manifest itself. But I really don't expect everybody to come back. So let me start with, so we're,
Just make some
oh, please, no, but better make them here then. It's,
some quick housekeeping announcements. Firstly, about restrooms. I think there is one restroom here, one restroom there, and one restroom behind. Okay, so this is for your information. The next is we'll be circulating some attendance sheets. We'll be circulating 2 printouts. One is for IISc, participants, and one is for non-IISc. The names have been alphabetically arranged. You can search through those lists and see where your name is. In case your name is not there, for whatever reason, there is some space at the end. Maybe you can just write your name session on each of the 4 days. Please make sure you are signing at the right place. Okay?
I've seen that. So I thank the organizers for providing this friction sheet so that my mouse is not sliding off the table like this. Okay. Now, yeah, so this is my home page. If you can't find it, just go to Google and search under M. Vidyasagar. At least as of now, I'm the most famous M. Vidyasagar in the world. Not the most famous Vidyasagar, but at least the most famous M. Vidyasagar. So that will take you to a bunch of options, including this page. And you can go to the teaching page, and there are a bunch of courses there, and you can locate the course I was mentioning. All the slides are there, not just the parts I'm covering here. There are also the course notes. Towards the end, the notes are not complete, but it should be of some use to you. Okay, so let's talk about this one. This module is a little bit more close to the solution of the problems. In the previous module, what we talked about is, okay, these are the equations we want to solve, but that doesn't tell you how to solve them. And this module is predominantly for that. And I'm covering 2 topics. One is called temporal difference and Q learning without function approximation. That's section 1. Section 2 is the same 2 problems, but with function approximation. So let's just see how it goes. So, as I mentioned at the end of the previous module, you have these 2 recursive equations, one for the optimal value, one for the optimal action value function. Both of them can be thought about as fixed point problems with some contractive map. So you can apply the iterations and wait for the things to converge, but in order to do that, you need to know the dynamics. Okay? Now, what if you don't know the dynamics? How do you solve the problem then? And that's basically what the temporal difference and Q learning methods are about. Okay. So let's just talk about a very basic problem. So you have a Markov reward process, not even a decision process. And so you have the reward vector R and the discount factor gamma, the state transition matrix A. And we have seen that the discounted future reward is the solution of this equation. V bar is equal to R plus gamma AV bar. Now, you are the person choosing the discount factor. I mean, there's nothing intrinsic about the discount factor. You are the one who decides whether 1 rupee tomorrow is worth 99% or 95% or 90%. So gamma is certainly known. But A may or may not be known. Okay? The reward is also known because you are the one choosing the reward for each state. Okay? But what if A is unknown? So think about the following challenge. You want to solve that equation when you don't know A. Well, you have to know something. Even if nobody gives you A, you have to have some information, otherwise you can't solve this equation. So how do we do it? So suppose what's the available information? You have the A matrix is unknown, but you have a sample path of a Markov process, which you can call X of t, with the state transition matrix A. So indirectly you are getting information about A because you have a succession of states and you know that the transition probabilities are governed by A. So one possibility is you take a pretty large number of samples, capital T, let us say, and then based on the observed sample path, you construct a maximum likelihood estimate. What's your best guess for A given the observations? And to substitute that into this equation and solve the equation with estimated A hat instead of the true A. And standard maximum likelihood theory tells you that as the number of samples capital T goes to infinity, then A hat of T converges to the true A. Therefore, the solution of this equation converges to the true value vector. That will be called the indirect method. Temporal difference is a direct method that calculates the estimate for V hat without estimating A. So there's some amount of confusion in both the adaptive control literature and in the reinforcement learning literature. What is meant by a direct method and what is meant by an indirect method? So my definition is an indirect method is one where you first estimate the so-called unknown parameters, substitute those into the equation you want to solve, and you solve it. A direct method is where you try to estimate the solution directly without trying to estimate the unknown underlying system. So temporal difference and Q-learning are examples of direct methods. So a little bit of notation in case you get confused. So you have the value vector V. So I'm going to use two notations interchangeably because in some situation one notation is better, sometimes the other one is better. So order the elements of the state space as x1 through xn and call this vector V as an n-dimensional vector. So you can think of the ith component of this vector as V of xy. So I call this capital V as the readout map. That means the value associated with the state xy. Okay? And it turns out to be beneficial to sometimes think of the vector as a function of x or a component. Okay? They're equivalent mathematically, but the notation becomes cleaner if I'm allowed to go back and forth between the two. Now this is the important observation which nobody tells you. I mean, it's kind of hidden in all the reinforcement learning literature, but nobody tells you this point blank. So I'm going to do it for you. Suppose there is a Markov process x of t with an unknown state transition matrix A. And you have at hand a vector V, given deterministic vector. Nothing unknown about it. Now what you want to do is to calculate the vector AV. You want to calculate the vector AV without knowing A. How on earth are you going to do that? Well, so suppose you have a Markov process, and what you do know is that its state transition matrix is in fact this unknown matrix A. So what you do is, look at the current component x of t, and then you calculate the same vector v, but at the next state v of xt plus 1. Okay? That is an unbiased estimator of the xt component of AV. So in other words, if currently the Markov process is in state x sub I, and the next time it is in state x sub j, all you have to do is to look at the vjth component of this vector, a jth component of this vector. That is an unbiased estimate of the ith component of AV. So that's xth component of AV. So this is kind of a one-step look ahead. Okay, well, unbiased just means that the mean of that is the right answer. That doesn't help you very much. You also need to know what's the variance. Well, the variance is no larger than 4 times the infinity norm of v squared. Now, I want you to notice a few things about this. First thing is, this is the infinity norm, not the Euclidean norm. Remember, I told you that in learning problems, you can get huge state spaces. So if a vector is huge dimensions, but the elements are small, then the infinity norm is going to be reasonable. But the Euclidean norm will be huge because you're adding up a whole lot of components. So the fact that this is the infinity norm and not some other norm is very significant. Second, how does the bound depend on the unknown matrix A? It doesn't. That's the point. You get a bound that's uniform in the unknown matrix. See, if I have a bound which assumes something about the unknown matrix, it isn't a very useful bound. But this is a universal bound. It holds for all matrices A. So those are the 2 points to remember. The bound is uniform in A, and even if the size of V gets bigger and bigger, the infinity norm is still manageable. Okay? So, with that in mind, let's talk about what is known as TD0 learning without function approximation. If you can see this grayed out bullet, there is TD lambda learning with function approximation. So in principle, you can do TD0 learning with functional approximation and TD lambda learning without functional approximation. Nobody seems to do that. So I'm going to use the simplest problem without functional approximation to motivate the method, and then we will go to the function approximation in the second part of the lecture. Now, this phrase TD, temporal difference, was coined by Richard Sutton in a paper in 1988. And I'm not completely convinced about the motivation for this phraseology TD. But that's okay. If everybody calls it temporal difference, it's as good a name as any other, right? So what's the problem? We have a known reward function R. R equivalently, we know the reward vector R belonging to R to the power of n. We choose a discount factor gamma. Because we're choosing it, we know gamma also. We don't know the state transition matrix of the underlying Markov process, but we do get to observe a sample path, x of t, whose state transition matrix is A. With this information, we want to solve this equation. Okay? That's the problem. So what we do is we generate a sequence of vectors, v hat of t, and update at each time. Equivalently, we can also think of it as a sequence of readout maps from the state space X to the set of real numbers. So how does it work? We start the algorithm with an arbitrary vector v hat of 0, just an n-dimensional vector. And at time t, we compute a temporal difference, which is just a scalar, the reward at the current state, plus gamma, the discount factor, times v hat of t at xt plus 1. This is the most important term to understand properly. V hat at t is your current guess for what you think the reward vector is. You calculate the component of that current guess, but at the next state, and subtract from it your current guess V hat of t at the current state. Now, why this weird difference? That's because of this thing. V at t plus 1 is an unbiased estimator of A times V. Therefore, this thing is an unbiased estimator of A times V hat of t. Okay? So that's the sample path gives you a way of generating this unbiased estimate. So then you take this temporal difference delta, and then you define an elementary vector E sub I where the only non-zero component corresponds to the current state. Then you update only the ith component of your current guess by multiplying it by the temporal difference and the so-called step size. Temporal difference is defined there. Alpha t, the so-called step size, the learning people also call this the learning rate. It's the same thing, okay? It's just depending on which world you come from. The people who come from stochastic process like me call this the step size. The people who come from the learning background call it the learning rate. It's the same quantity. So the idea is that this is your error. Why is this the error? Suppose that your current guess V hat is perfect. It in fact is the true vector. Then this quantity would have zero mean. Doesn't mean it's zero because of the underlying randomness, but its mean is zero. So in principle, this is a zero mean vector. On the other hand, because V hat, your current guess, is not necessarily the correct answer, there is some bias as well, and that gets corrected for that. And why do you have the step size? Because as learning goes on, usually you want the step size to grow smaller and smaller in order to guarantee convergence. So this is the TD0 algorithm. You may say, what is the zero? We'll see a little bit later. So the general convergence theorem for TD0 is that if the step size sequence is square summable, and almost surely the second condition is true, then the V hat of t converges almost surely to the true vector. Okay. Because everything is random, let's go back to the previous slide. You are updating at each time instant only one component of your guess. You have a current guess V hat, which is an n-dimensional vector, but at time t you are updating only one component, and the component you are updating is the one corresponding to the current state. Others are not updated. So it's kind of obvious that your Markov process has to visit all the states infinitely often in order for this method to have any hope of converging, right? And one easy way of guaranteeing that is that the underlying Markov process is an irreducible Markov process. Okay, it's a very basic fact that people should know, that an irreducible Markov process visits each state infinitely often, and the fraction of time it spends in each state is equal to the corresponding component of the stationary distribution. Now there's one more important step that you need. You want the step sizes to be square summable. Okay, that's fine. But this one says you add up the step sizes, but you don't add up all the step sizes. You add up for a component I only the step sizes every time you update that component. And that summation has to equal infinity. Now that is a deterministic sum, but this is a random sum. Do you see that? This is just a summation of the step sizes. But because x of t is a random process, the summation is also a random process. So you want the summation to equal infinity almost surely. And the convergence of the estimate is also almost sure. Now, if you don't know what all this means, please educate yourself, because randomness and stochastic processes are absolutely crucial to understanding reinforcement learning. You can't do without it. So now you may say, well, okay, how on earth do I verify this second condition? Because it seems to involve a random sum equaling infinity. Well, I have to tell you that I actually made up some slides. It was getting too messy. So finally I just said, there are ways to verify the second condition. You can look at my course note,
Sir,
where I can actually show you how to do this.
so
Yeah.
why in case of non-deterministic, why is alpha t is not square, and in case of deterministic it's square?
I don't know why. Read the book and find out. That's all I can tell you. Why is it not squared? You have to read the book and find out. You had a question? Yeah.
Yes, sir. So basically, the second condition, right? The intuition is that you will be visiting the same state xi infinitely often, so that you can learn about the value of the state. But wouldn't that cause a bit of chattering, because your alpha t is positive even when you visited it infinitely often? Like, would it still converge?
So the first condition guarantees that alpha of t has to go to 0. Because alpha t doesn't go to 0, there's no way this condition will hold. But you don't want alpha t to go to 0 too fast. And in particular, what you want is that each state, whenever you visit, if you accumulate all the step sizes, when that state is visited, that has to diverge. That's the intuition. Sorry for all this coughing. Yeah, as to why this is alpha t and not alpha t squared, well, as I say, you just have to, that's where the stochastic convergence results come in. I mean, my course was called Stochastic Algorithms for Non-Convex Optimization and Reinforcement Learning. Okay, so you have to see why the two can be handled using a common framework, and you will see this condition coming up over and over again. Okay, now let me talk about Q-learning, again without function approximation. Let me just remind you what the action value function was for a fixed policy. It's defined by the expected value of the summation starting at an initial state xi and the initial action xk, where from time 1 onward to implement the policy, right? And let me remind you, it can be viewed as a large column vector or a matrix. And this was the same equation we saw before the break, that you want to solve this equation here, this implicit equation. Once you have solved it, the optimal policy comes very easily. For every state, the optimal action to take is the argmax of this quantity, okay? So the key is to solve this equation. So how do you do that? So this is very famous Q-learning algorithm, proved in 1992, so more than 30 years ago. And again, we have the same challenge. How do you solve this equation without knowing those numbers? Okay, you don't know the dynamics of the MDP. So how do you solve this equation? So what we have is that these matrices themselves are unknown, But for even given state and given action, you generate the next state with a conditional probability equal to the ith row of this matrix A of UK, where x bar is the current state. So basically what this is the decision version of the previous assumption. In the TD learning, we said, I have a Markov process. I don't know what A matrix is, but I know that the Markov process is distributed according to that A matrix. Here I'm saying, whatever is the current action, the next step is determined on the basis of that Markov process, associated Markov process A. But then at time t plus 1, you may have a different action. So xt plus 2 will have a different distribution and so on. So this is all you need. So what do we do here? So this is a rather complex looking algorithm. What you do, just one second. Okay, so what you think this thing fell off, no? Okay. Oops, not coming off again. Okay. So here you start with an initial matrix. In the case of TD, which is only trying to determine the value function, you start with an initial vector. Here you start with an initial matrix because the rows are the states and the columns are the actions and some initial state. Okay. So at each time you choose some initial action, choose some current action u of t, and let the Markov process run for one time step. And our assumption was, given the current state and the current action, the next state is distributed according to this matrix A of UK. Okay? So then what happens? You get the next state x of j. So there are three things to keep track of here. The current state x of I, current action UK, and the next state x of j. Okay? Then you update only the xi UK component of q. You don't update anything else. So for that component, xi UK component of q, you multiply it by the reward of xi UK plus gamma of vt at xj. And what is vt? Vt is this function here. And xj is the next state you get, minus qt of xi UK. This looks like a very confusing formula, but just remember that this quantity vt evaluated at the next state is the maximum likelihood estimate of this vector multiplied by a. Okay? That's the key to this algorithm. And because of that, you only update one state action pair at each time instant. You leave the rest of them alone. You don't change them at all. And if you keep doing this, the convergence theorem looks very similar to what it was earlier. This beta of t is the learning rate or the step size. So you want the step sizes to be square summable. And in the temporal difference learning, we had the step sizes for each state add up to infinity. Here you have to say each time a state action pair is visited, those step sizes diverge. If this is true, then the resulting estimate converges to Q star almost surely. Now, in order for this condition to hold, every state action pair must be visited infinitely often. Okay. Now, if you look at the previous slide, okay, here is the current state. Choose the current action. Well, how do you choose it? The algorithm doesn't give you a guide. So you have to choose it in such a way that every state action is visited infinitely often. So one possibility is to use a randomized policy for choosing the next action, so that no matter what the current state is, every action has, let's say, an equal likelihood of being chosen, something like that. Okay. The distinction I'm trying to make is the next state is given automatically, but the next action you choose. So you have to take advantage of that freedom to make sure that this condition is satisfied. And there are more details, but I didn't want to go into too many details because it will be overwhelming. But essentially, you are trying to guarantee that this infinity condition holds by suitably choosing the action. Okay, now let's talk about learning with function approximation. How shall I say? Now the fun times are over. What I mean by fun times are over, from now onwards, unfortunately, the formulas are going to get really messy. Okay, the rest of module 2 is fairly messy, and module 3 is really messy. So I apologize for that ahead of time. I've tried to simplify things as much as possible, but there is this famous saying of Einstein, which I'm sure you know. He said, things should be made as simple as possible, but not simpler. Do you know that one? So I think I've sort of hit that limit. I don't think it's possible to make things more simple than what I've done it. But I'm just cautioning you that from now on, things are going to get more messy. Okay, so what is TD lambda learning with function approximation? Well, you remember, this is the quantity you're trying to calculate. We have xi, where R is the rewards, and A is the underlying state transition matrix. So what is the extra wrinkle? The extra wrinkle now is, I have this function V, which is a map from the state space to Rl. So you can think of this as an n-dimensional vector, where n is the number of states. And I've told you that in many learning problems, n is a very large number. So you don't want to carry this huge dimensional vector. So what you do is approximate V by another function V hat, which maps the state space times R of D, which is called the parameter space, into R. So for each state and each choice of parameter, V hat of xi theta is an approximation for the true value. Now so typically, I should have mentioned this, D is much smaller than N. Obviously, you're trying to simplify the problem. So the set of adjustable parameters is far smaller than the number of states. Otherwise, what have you achieved? Okay. Therefore, because you are using this lower dimensional approximation, there is no hope that you will actually find the true value. You just have to do the best you can. Okay. Now, for the moment, I won't insist that V hat is a linear function of theta, but a few slides later, I will insist that. Okay. So, same assumption as before. You have a sample path X of the unknown Markov process, and at each time you observe the reward also. And then you have the temporal difference, okay? No difference till now, exactly the same as before. Now the conventional TD is replaced by this extra term. In the conventional TD0 without function approximation, what happens? the function v hat is v itself. So it's essentially like taking the identity matrix. Therefore, the gradient of v hat of xt with respect to theta just becomes the column vector, 1 in the current state and zeros elsewhere. So if you replace this by e sub I, you get back TD0. But when you do function approximation, you have this gradient. So one of the things you gain, one of the things you lose. One thing you lose is in TD0 without functional approximation, this vector has only one non-zero component. So you're only adjusting one component at a time. There's no reason why this vector has to be sparse. So you are in principle updating every parameter of theta. See, what you're adjusting is not v, you're adjusting the parameter theta. So that's both good and bad. If you're adjusting every component at every time instant, maybe you'll converge faster. That's the good news. The bad news is you cannot hope that this will converge to the true answer because you are approximating a high dimensional vector by a lower dimensional vector. Okay? So let's go from TD0 to TD lambda. So the difference is that in the previous version, we took the step size alpha, we took the temporal difference delta, and multiplied by the gradient of this approximating function. Here, you have the same step size alpha, same step size, same temporal difference delta, but now you multiply by a more general vector z, which is called the eligibility vector, and it is defined by this fairly nasty looking summation. From time from 0 to t, gamma, which is the discount factor, lambda is a parameter you choose. Because this is called TD lambda updating, so you can choose whatever lambda you want, some number between 0 and 1. So you raise this to the power of t minus tau, and then add up all the gradients. So what is this thing? Well, instead of looking at only the current gradient, you take a weighted sum of all the previous gradients. And because whatever lambda is, gamma is definitely less than 1. Therefore, this coefficient gamma times lambda is less than 1. So the distant past derivatives get less and less weights. Okay? And so this is the quantity z that you multiply alpha t delta t instead of just the plain old current gradient. Okay, now you look at the sum and you say, do I really need to keep track of this infinitely long tail? And the answer is no, you don't, because there is a simple linear recursive relationship between the current z and the previous z. You can just look at that and you can see that it satisfies this equation. So all you really need to keep track of is the previous eligibility vector and the current gradient, and you can calculate the current eligibility vector. Incidentally, this word eligibility vector was also introduced by Sutton. There must be some machine learning motivation for this phraseology. I have to tell you honestly, I don't really know what that is, but it doesn't matter. Just a name anyway. So now what happens if you put lambda equal to 0 and if you define lambda times gamma to the power of 0 to be 1, then the whole term collapses to just the current gradient and you just have TD0. That's why this is called TD lambda. TD0 is a special case with lambda equals 0. Now, at this point, you're pretty much stuck. If you want to do any more analysis, you have to sort of assume something about the nature of the approximation. Till now, I've said v hat can be any function, but now I'm going to specialize to the case where it's a linear approximation. So I assume that the approximate vector v hat is some matrix phi transpose times the parameter vector theta, where phi is a matrix of dimension d by n. So n is the number of states and d is the number of parameters. And obviously you want d to be much smaller than n so that you make the problem simpler. So that makes the problem simpler, all right, but there's no reason to assume that the true but unknown value vector is going to look like this. The true but unknown value vector may not belong to the range of the matrix phi. Therefore, even if this algorithm is very well behaved, it may or may not find the right answer. Anyway, we'll come to that in a few slides. So phi has full row rank so that none of the components is redundant. That's a kind of a simple technical assumption. So as I mentioned, V bar is the true value vector. What do these converge to? Let's see. So what is the difference between what we had earlier and what we have now? Well, the thing is, if V looks like this, then what is the gradient of V? If the current state is x of tau, then the gradient is just the corresponding column of this approximating matrix. You see what I'm saying? I see a few blank faces here, so let me just explain. What is this gradient? If V is just a matrix multiplying theta, it's just the corresponding column, that's all. And that's all we're saying here. So the formula looks a bit cleaner. All you're adding up is columns of this basis matrix capital Phi with various time varying coefficients. So this is the same formula you've seen before, except now the Z is defined by this formula. And the recursive relation looks like this again. Okay. Now we can ask a few questions. What does this converge to? Well, it turns out that there's a very neat result that helps you to somehow answer this question. If the unknown transition matrix is irreducible, let mu denote the unique and strictly positive stationary distribution. Sorry, there's a typo here. The m subscript m, there's a dot, anyway, it's a norm dot m is what is. This thing is supposed to be norm, the subscript of m. Okay, anyway, sorry. So suppose you define a vector norm as V transpose mv to the 1/2, where m is the diagonal matrix of the components of the stationary distribution. Then it can be shown that the matrix A is non-expansive with respect to this norm. That means you take any vector V, the m norm of AV is no larger than the m norm of V. Okay. Now, we already know that this is true if I make this the infinity norm, because A is a state transition matrix. But this is more useful for future purposes. Now, this is an abstract result because you don't know what the m norm is. You don't know what the m norm is because m depends on the stationary distribution, but you don't know the stationary distribution because you don't know A. So this is an abstract result that's useful for proof purposes, but not computational purposes. Okay, now let's talk about this projection map, pi. What this pi does, you must have seen this thing in your simple linear algebra courses. You take a vector A, multiplied by phi transpose, phi transpose inverse, phi transpose m, that gives you a lower dimensional vector which belongs to the span of the matrix phi, and it is also the best possible approximation to the given vector A with respect to the m norm amongst all matrices in the span of phi. It's just a simple least squares formula. You probably have seen it with m equal to the identity matrix. Sticking in this m makes the formula a bit more messy, but not a whole lot. Okay. So why do we talk about pi? So the pi A is the closest point to A in the subspace phi t of Rn. And suppose that V bar is the true but unknown value vector. Since your approximations will all belong to this space, there is no reason to assume that your iterations will converge to V bar. That's not going to happen. But at least you can hope that it will converge to the best possible approximation to V bar in this subspace. Is that true? Well, unfortunately, even that the answer is no. Okay, so we'll see. So this limit behavior of this TD lambda updating is that if the step sizes diverge and step sizes are square summable, then the parameters theta t converge almost surely to a unique vector theta of lambda. You can say more about theta of lambda, but I decided not to put all that material in here. But this equation is the crucial equation. If this is the limit, so phi transpose theta of lambda is the approximate value that you have got, right? The difference between the approximate value and the true value as measured in the M norm is bounded by this constant times this number. Okay, let's look at this equation. What is this number? This is the best possible error, best possible approximation to V bar in that subspace. So you cannot possibly do better than this. Unfortunately, you look at this ratio, it's not very hard to convince yourself that is always greater than, is always more than 1. Since phi t times phi lambda is in the subspace, this is the best that you can hope to achieve, but this new vector is bounded by this factor times its minimum, so this is greater than 1. Okay? So this is the extent to which TD lambda learning fails to achieve the best possible approximation. So how do you improve the situation? Well, one possibility is to make D, the dimension of the approximation parameters, higher and higher. But that's kind of defeating the purpose, because you're trying to take a large dimensional problem and squash it into a lower dimensional problem. So you don't want to increase D, you stick with D. Second thing you can do is to let lambda approach 1. So suppose you plug in lambda equals 1, then the ratio equals 1, right? So then you get the best possible approximation. That sounds like a quick fix, except for one small problem. As you let lambda approach 1, that means, first of all, if I go back a few slides, please bear with me. These are the eligibility vectors. If you make lambda closer and closer to 1, the tails are becoming bigger and bigger. They don't decay as fast. So you have to keep track of a lot more stuff. I'm here. I mean, the simple recursion is hiding the fact that the tails don't actually decay very fast. And second, this is the most important one. All this convergence analysis only talks about what is the limit. It doesn't talk about what is the variance around that limit. That's another whole body of literature. I'm just summarizing it in one line, saying, but at the cost of higher variance. I'm being a bit disingenuous because there's a lot of theory to analyze what is the variance of the sequence around its limit. Basically, you can apply some central limit theorem and figure out the variance, and it just gets higher and higher as you get lambda closer and closer to 1. So basically, you have a trade-off, but it's quite a useful thing to know, this theory. Now, let me just tell you very quickly about deep neural networks, and then as you can see, the last bullet, deep Q learning. So this is the standard multidimensional multi-layer neural network, these neuron characteristics F1, F2, F3, and so on, they're all neurons of some kind. Originally, this was used with perceptrons, but they don't all have to be the same. So way back when, this was the perceptron, simple sine function, and this is the sigmoidal nonlinearity. And this is not used very much nowadays because as you get away from zero, the gradient goes to zero, you see, there and there. So now people are much more using things like rectified linear units or leaky ReLU. And so a deep neural network has, say, D inputs and N outputs, where D is the number of parameters and N is the number of states. So the idea is that these, I should actually have changed these x's to thetas basically. Anyway, so you put in the parameters and then, I have it correctly. You have an n-dimensional input and the number of adjustable parameters, those are the thetas, and then you finally get a function that maps Rd into Rn. But the difference between the earlier situation and now is that a neural network has many more adjustable parameters than it has input. So this is kind of running counter to my linear approximation of paradigm where the parameters are fewer in number than the state space. Here, I have more parameters than states. So the idea is that you achieve more richness of representation. Also, theta is not linear in theta, so this is obviously a typo. What do you think is the correct sentence? Anybody want to take a guess? No brave souls want to take a guess? Okay, the correct statement is also V is not linear in theta. V is that map, which maps the input to the output. That's not linear in theta. Okay, now what about deep Q learning? You might have heard about it. So, the key observation for deep Q learning is that if you take a Markov process and if you apply a policy, the resulting state-action pair is also a Markov process. If the policy is deterministic, this is not very interesting because once you specify X, U is known. So what kind of a Markov process is that? Meaning, the conditional probability of U given X is just one component. That's not that interesting. But if you use a probabilistic policy, the fact that Xt Ut is a Markov process is more interesting and it has more likelihood of exploring all possible state action pairs. So the basic idea is to say, and this is not a very precise statement, but I'm trying to make it very easy for you because I have only about 10 minutes in this module. Q iteration is basically like computing the value function for the joint Markov process of X and U. That is an interpretation which I didn't have time to derive, but that's one rederivation which is very useful. If the dynamics are not known, and so what you have now is this V hat, which is the approximation of the true V determined by the parameters. So it's a function of the current state as well as the parameter vector. So this is the same thing you have seen several times already. The temporal difference between the current reward, the current approximation, and the current approximation but evaluated at the next state. And then you multiply it by the gradient of this V hat with respect to the parameter vector. And to calculate this gradient, you use backpropagation method. Okay? And if you want to do TD lambda version rather than TD 0 version, you keep summing the previous gradients as well. So this is the same algorithm before, except that this v hat is not really v hat, it's for the action value. I didn't want to change the notation because I wanted to bring out the commonality between Q learning and value learning, but the same idea. Convergence results, almost nothing. Lots of simulation, but there are few papers when you have ReLU as your neuron, because it's essentially a piecewise linear equation. So you can do some analysis, but for more general, almost no convergence result. But it does seem to work in practice, so people use them a lot. So lots of problems to work on. That's the end of this module. Okay, we'll take a 5-minute leg stretching break unless there are some questions on that. All right, so we'll reconvene in about 5 minutes.
About the TD lambda learning, so when you mean the Markov chain is irreducible, you mean that is under all stationary policies?
No. In the TD lambda, there is only one A matrix because it's a value determination problem. Now you're asking a very good question that I didn't want to get into, but since you've asked it, let me answer it. Please bear with me while I cycle back. Okay, finally I got this thing. Now, the question you're asking is, suppose I have all these A matrices, one for each action. And when is it true that for all possible policies, the resulting A of pi is also an irreducible matrix? So clearly a simple necessary condition is that each of these m different matrices have to be reducible. That means you apply the same action at each time, you get an irreducible matrix. But remember, when you have a policy, you're jumping around between actions. You want to know, no matter what policy I choose, is that resulting matrix A of pi irreducible? So the answer is, that's an NP-hard problem. So it's very bad news. So in one of my papers with Professor Rajiv Karandikar, we have got around this problem by requiring only that for each fixed action A is irreducible and proving convergence. Do you understand the distinction I'm making? You asked a very good question. For all possible policies, is A of pi irreducible? I mean, there are people who make assumptions like that. And I personally think those kinds of papers are a bit dishonest because we make an assumption verifying which is an NP-hard problem, then what's the use of that theorem, right? So that's why we got rid of that. And we have a way of doing it so that you only assume that each of the m different fixed actions will give an irreducible matrix. But thank you for the question. It's a very good question, actually.
Thank you.
Okay, if there are no more questions, we'll take the leg stretching break. And
Sir, I have a question.
yeah.
So there are hidden Markov models which are like models used in speech and NLP applications. So they also have a property like you have order, which is like how much of history you consider. So can I somehow see it as this TD learning with lambda parameter? Can I relate that with HMMs? Or basically, is there some connection between HMMs and TD learning?
No, the simple answer is no, because when I have a hidden Markov model, That is also called in this lingo POMDP, partially observable Markov decision processes. Now, the whole point there is that when you have a hidden Markov process, the underlying Markov process is hidden. So you cannot measure X. So that makes theory very complicated. So basically, nothing I've said will work in that case. Now, that doesn't mean nothing is known. I'm just saying that whatever I've said doesn't apply to that case. But you look under POMDP, you'll get a whole bunch of papers on that.
Thank you, sir.
Okay, anybody else? All right, so let's take a break and we'll come back. So we're about 15 minutes behind. So I guess we'll finish it about, let's see. So it's what, 11:45, so about 12:45. Is that a problem? Okay. So I apologize ahead of time for the messiness of the third lecture. I was telling Professor Tope that you're going to see a blizzard of equations. So what I'll try to do is to let you navigate through the equations at your own leisure, because I'm going to leave these slides behind. I'll fix those couple of typos I discovered, and then you can read them through at your leisure. I'll just try to give you the high points of what is happening. All right. So in this third part, I was asked to talk about two different topics. One is called actor-critic methods, and other is called Monte Carlo methods. And you can see the outline here. So we'll start with average reward processes. Well, before that, I just wanted to mention to you the somewhat bizarre terminology, actor-critic. You know, you can imagine that a lot of the phraseology comes from the world of learning, not necessarily the stochastic process community. And I think it's perfectly fine in the sense that if you're like me, you come from the stochastic process world, you can just simply adopt the learning theory community terminology. So they have called it actor-critic. So this has to do with something called the policy iteration approach, which I did not cover because I didn't have time. I had only 3 hours. But the basis of the policy iteration idea is you pick a policy, calculate the value, use that to improve your policy, and you calculate the value, and so on and so forth. And you can prove that this method will converge. Except just like a scorpion, there is a sting in the tail. And the sting in the tail is you have to actually calculate the value for each policy exactly. This theorem collapses if you don't calculate the value of each policy exactly. Well, if you see all the mathematics until now, calculating the value for any one policy takes infinite amount of time. So how do you get around that? So you try to say, well, why can't I just approximately compute the value corresponding to a given policy and use that to update my policy? And there are some simple examples in the machine learning literature to show that if you don't do this in a smart way, things will just blow up. Do you understand what I'm saying? You say, why is it necessary for me to wait until the value is computed exactly? I'll just use the approximate value and hope it is good enough. That doesn't always work. So you think about, and by the way, I mean, books do give these examples why you have to be careful. I'm just not doing it in this lecture because of lack of time. So you can think about actor-critic methods as a way of updating the policy based on approximate values, which doesn't blow up. Okay, that's the way to think about it. Unfortunately, it does lead to a whole bunch of messy equations, but you can cope as best you can. And from whatever little I have seen, the behavior, the actual theory of actor-critic algorithm seems to have been analyzed mostly for average reward problems. So I'll tell you a little bit about those. So what have we decided, what have we studied until now? We looked at these kinds of situations. We start with an initial state, let the Markov process evolve, discount future rewards by factor gamma, and then sum it, and then take the expected value. In the case of average rewards, there is no discount. So the rewards are just adding and adding and adding, so potentially they could blow up to infinity. So how do you prevent them from blowing up? You take the average, right? So this is not the same as that. For one thing, in this, a reward that comes later has less value than a reward that comes now. In this, it doesn't matter when the reward comes. Just think about it. Suppose you look at the first 10 rewards and you shuffle them around, permute them. What happens to this sum where I put the cursor? Well, nothing. It's the same sum. But this sum is going to be different. Okay? So you have to have different methods of analysis for the two situations. So let's define C star to be the limit of the average reward, assuming that my initial state is distributed according to some probability distribution phi. Okay? So strictly speaking, I should put C star as a function of phi, but I don't because of the theorem on the next slide. Suppose S is the set of all probability distributions on X. Suppose further that A is irreducible and let mu be the unique stationary distribution, then that quantity C star is well defined for every initial distribution, and it is equal to mu, which is the stationary distribution, times R, which is the reward vector, no matter what the initial distribution is. Okay? So C star doesn't depend on phi. Now, this result is very intuitive, but the proof is fairly messy in the sense that why does the C star look like this? Well, if it's an irreducible Markov process, every state is visited infinitely often, and the ratio of time that each x sub I is visited is mu sub I. So obviously the average reward is going to be mu sub I times the R sub I. That's all this says. But to prove that is fairly messy. Okay. I'm just going to do one thing, if I may. I'm just curious whether the power is... Oh, no, it's fine. Okay. I was a little bit worried that yeah, these are the messy equations I was warning you about. Okay. So the reward of the average reward process does not depend on the initial distribution. Okay. So what is an average reward decision process? The previous one was just an average reward process. There's nothing to decide. Okay? So as before, we have R, which is x cross u into real numbers. So for each state and each action, you get an associated reward. And for reasons which I'll explain later, we have to use probabilistic policies. So let S of u be the set of probability measures on the set u. So pi of theta is a map from the state space X to the set of probability distributions u. And on top of it, I'm going to put in one more parameter theta, meaning I'm not considering all possible probabilistic policy. They are parameterized by some vector theta, which is a much lower dimension. So pi of xi uk theta is the probability that the action you take is uk, given that the current state is xi and the current parameter is theta. So the policy is not only probabilistic, but it depends on some adjustable parameter theta. Okay. So under a policy pi of theta, the state transition matrix is given by this. Okay. And why is that? Because for a given action u, this is the transition probability. But the probability of your choosing an action u is given by this quantity. So you average over all the possible actions, you get this, and believe it or not, this is actually a transition matrix, and that the state transition matrix. So call this matrix A of theta. Why A of theta? Because each choice of your parameter vector theta gives you a policy, and that leads to this matrix A of theta. Assume that it is irreducible for each theta. This goes back to the question you were asking, right? So you have to choose this parameterization a little bit carefully, because buried in this analysis is this assumption, which is not that straightforward to satisfy, right? And let mu of theta denote the corresponding stationary distribution, right? Now, mu of theta is the probability distribution of x under this policy. So this is the A, and this equation just says mu times A is equal to mu, except this thing in the square brackets is A. Okay, this equation looks a lot worse than it really is. It just says for a given matrix what's the stationary distribution. Okay. Now for a given theta, the reward is this, because this is the policy and this is the reward for each state action pair. Okay. So now the average cost for a parameter vector theta looks like this very messy formula. What is this? This is the reward under the policy pi multiplied by the stationary distribution for the parameter vector theta. So what do you want to do? What's the decision? The decision is to choose the parameter vector theta in such a way that C star of theta is as high as possible if it is a reward, or as low as possible if it is a cost. Now we have got many layers of complexity here, and I'm kind of squashing them all into one. First of all, I'm saying that the policy is permitted to be probabilistic. Second, I'm saying not all probabilistic policies are permitted. They are parameterized by some vector theta. And what I'm trying to do is to find the best possible parameter vector theta. Okay. Now this last bit simply says that once you fix the policy, x theta ut is a Markov process, and the stationary distribution of this joint process, I'm calling it as eta sub theta. It's not very crucial. It's basically multiplying the distribution of x itself by the distribution of u given x. So don't worry about it too much. But this is the key point. You want to maximize or minimize that. Okay, so what is the analog of the action value function? Now this is something that's somewhat unique to average reward processes. I'd start in the initial state x sub I, initial action uk, and from time t onwards, time 1 onwards, I implement the policy pi, and what am I adding up? I'm just adding up the expected value of the reward at time t minus this cost C star. Now, pay some attention to this summation. Why should the summation exist? Remember, there is no averaging here. If I just need to remind you, you don't have to worry about the existence of this limit because you're adding up huge number of terms, but then you're dividing by t. There is no 1 over t here. So does this summation even make sense? And the answer is yes, it makes sense, but I'm not going to prove to you why it is. If you look at the course note, you will see why the summation is well defined. So this is the analog of the action value function for average reward processes. And this thing satisfies this recursion, which should sort of look familiar. Okay? Now, we come to a very famous theorem called the policy gradient theorem. Absolutely a mess, but it is a very, very good result. So what does it say? We want to maximize C star of theta. Well, how do you maximize or minimize it, depending on what you want to do? If you had a nice formula for the gradient, you can use your favorite method. So the whole objective of what I'm calling as the blizzard of equations is to get an implementable formula for this gradient, okay? Under the assumption that you don't necessarily know the state transition matrices, okay? I mean, it's easy to get lost with all the formula, but that's the fundamental idea. How do I calculate an approximation to this gradient without knowing the underlying dynamics, okay? So just keep it in mind, and that should help you get through this equation. So this policy gradient theorem, due to Sutton and the company, I think Satinder Singh, there's one more author, I don't remember. Anyway, they proved this formula. The gradient of the optimal cost with respect to theta is given by this thing. No, I think there's no C star, just C. That's wrong, just C. Just the gradient is this. So what is so special about this formula? There is no term of this type. In other words, remember the state transition matrix A depends on the policy, and the policy depends on theta, and mu depends on A. So at each state things are getting messier and messier. So if you actually had to calculate the gradient of the stationary distribution with respect to theta, you're basically dead. I mean, there's no way in which you can do that. In fact, it's not even a differentiable function in general. But in this formula, there is no term of this kind. So this is a very useful term. So let's look at it more again. So the gradient, again, sorry for the typo. The gradient is the stationary distribution mu for a particular parameter. How do you know it? Well, you don't know it. However, by watching the evolution of the states and calculating what fraction of the time the trajectory is in each state, you get something that is a reasonably good approximation to the stationary distribution. Are you with me? If you have a Markov process which is irreducible, And if I ask you what is its stationary distribution, you just see how often it is spending in each state, and eventually that begins to look like the stationary distribution. So you can get a decent enough approximation for that. What about this gradient? Well, you are the one choosing the policy, so of course you know what that gradient is. So that's easy. Now you have this q of theta. That's the troublesome one because you don't know anything about it. So you have to figure out a way of approximating q of theta. So it turns out that, just as we had done before, if you calculate this at the next time instant, that's an unbiased estimator of q of t, q theta of xt. Now, in this paper by Konda and Tsitsiklis, they add yet one more layer of complexity, which is that they choose this theta to be some random so where are we here? An approximator for this q hat of theta. Okay. So given a parameter theta, you don't try to calculate this quantity exactly. You try to approximate it by some function. So you see what's happening here? There is the true action value function, which you can observe with an unbiased estimator, just by replacing xt by xt plus 1. Then you try to approximate it in a lower dimensional space. Then you choose an approximation for the approximation. And if you read the papers, you will see why you need so many layers of approximation. And then what you try to do is to choose an element in the sample space so that you can minimize this quantity. Then I'm sticking to their notation omega. This is a bit unfortunate notation. Normally, I tend to use omega for the sample path descriptor. This is not the sample path descriptor. This is just a parameter. But I'm sticking to their notation. Anyway, the bottom line is, if you can calculate the gradient of j with respect to omega, you just simply can adjust omega t plus 1 minus omega t to be some multiple of this gradient. Okay, I warned you that this is going to get very messy. I don't even know where I should actually start. I'm actually thinking that I should just skip the rest of it. So you get this massive formula. So I think I'll go to the summary, and people are going to get totally lost. So here's the idea though. Here's the summary of all those messy formulas. Your unknown action value function is approximated by this function. And since you can get an approximation for this gradient, you can use that to update theta. And if your approximation is good enough, you can hope to converge. But the third bullet is the key. This was hidden in all those equations I skipped. But the point is that the theta is an approximation for the value. This omega sub t, I'll just show it here. This omega is a way of approximating this thing. And there is a coupling that is introduced. This coupling is buried in all those equations. But the key consequence of the coupling is that as the policy approximation gets updated, so does the value approximation. So if you remember what I mentioned, your idea is to use an approximate value to improve your policy without running into trouble. And all that huge number of equations introduce the coupling in a manner that you don't get into trouble. Okay, so this is all a precursor to actor-critic method. So this is all just the policy gradient theorem, that's the bullet. Now let's go to actor-critic method. So just repeating the point that I mentioned, that for any fixed policy, not only is X a Markov process, but so is the joint state action process. And if mu of theta is the stationary distribution of X, this is the stationary distribution of XU. So the clever idea of these two guys, Konda and Tsiklis, is they view the state action Q as a matrix. Now you know that between any two matrices you can just define an inner product. For example, you can just take the component-wise inner product, and that's called the Frobenius inner product. I think some of you probably know that. So the cleverness of these people is they don't do that. They define a very special inner product with respect to eta. Okay, this looks like the component-wise inner product, except that each component is weighted by eta sub theta, where eta sub theta is this quantity. It's the stationary distribution of the state action pair. Okay, so you're taking the inner product of two possible state action matrices, not with just the natural Euclidean inner product, but with respect to the corresponding fraction of the time that the state and action spend in each state action pair. And then what they show basically is that the gradient of the optimal cost with respect to the ith component of the parameter vector theta is given by this inner product. Okay? And they show that you don't really need to know this unknown state action matrix in general, but only a projection of it on the space spanned by omega and theta. So for example, if you choose linear parameterization of policies so that you have a bunch of stationary, a bunch of column vector C, and you choose theta sub L. Now, you have to be careful here because remember, a policy is a set of probability distributions. So even if you choose the psi sub I to be probability distribution, unless you choose theta to be non-negative and to add up to 1, pi is not going to be a probability distribution. But that's a very easy constraint to put. In other words, there's no reason that you have to maximize over all possible thetas. You can maximize over all possible thetas belonging to the d-dimensional simplex, non-negative components adding up to 1. Okay. Anyway, so this means that the partial derivative of pi with respect to theta is just the corresponding component divided by theta. So to find the optimal choice of theta, it's not necessary to know the full function Q, only it's enough to know its projection. It also belongs to lower dimensional subspace. I know I'm going too fast, and I didn't want to do that, but believe me, I tried to make this as comprehensible as possible, just give you the highlights so that you can read the literature and hope to get some idea. So they approximate it in this fashion, again a linear summation. And let me just cut right to the theorem. There are two updating rules, one for the optimal cost and one for this coefficient zeta. And they have a step size beta. And the policy is updated with a different step size alpha. Again, there are too many equations here, but the point is that your estimate for the cost, which is the critic, is telling you what for a given theta is the cost, but it is approximate. You don't know it. That is updated using a step size of beta. Based on this approximate value, you have an adjustment for the parameter theta, which has a different step size alpha. And what they show, and this is what I really wanted to get to. I mentioned that if you use approximate values to improve your policy, you can get into trouble. So how do you avoid getting into trouble? You avoid getting into trouble by updating the values more slowly than you update the policy. So ignore all those equations. This is the key slide. Remember, alpha is the step size for the theta, which means the policies are being approximated according to theta. Beta is the step size for C. That is the step size for approximating the value. So the condition is the alphas are diverging, betas are diverging, alphas are square summable, betas are square summable, and this is the key condition. The ratio alpha t over beta of t approaches 0 as t goes to infinity. Then you can show that the limit of the gradient of c star of theta with respect to theta equal to 0. So the importance of that condition is that the policy is updated more slowly than the action estimate. Okay, that's how you avoid getting into trouble. So in other words, if you update the policy each time you update the estimate of the action, then you're going to be in trouble because your action estimates are varying too quickly. You kind of let things settle down a bit before you update the policy. That's roughly one way of thinking about it. And also, you see, you've only proven that the gradient approaches 0, which is not quite the same as showing that you have maximized it. It's not even like showing that theta itself is approaching a stationary point of theta. I mean, there are lots of things involved here. For example, in their original paper, they don't even have lim. They have a lim inf. So anyway, the bottom line is that this is a very, very technical area, and I know far less about it than the two people sitting in the audience, namely Professor Bhatnagar and Professor Tope. So if you have any questions, direct it to them, not to me. Okay, now, jokes aside, this is all I wanted to say about actor critics methods. I know this is the least comprehensible part of the lecture. And in fact, I wanted to switch the order of Monte Carlo methods and actor critic methods. But I didn't do it because I wanted to leave you with a good taste. Just before lunch, I wanted to give you something that you can actually understand, not this snowstorm of formulas. Okay? So let's talk about Monte Carlo methods. For value estimation, you use Monte Carlo method. So what is the setting? Again, same thing as before. You have a Markov decision process with a known state space, known action space, but unknown state transition matrices and an unknown reward function. And you fix a policy, pi. So there is no decision here. It's just a value estimation problem. But this third bullet is the important difference. Until now, I have been saying that these matrices A are irreducible, right? I'm now doing exactly the opposite. I'm saying that each of these A matrices have absorbing states, which means that once the process goes and lands in one of those states, it gets stuck. It cannot get out. So when that happens, that is known as an episode. An episode is any sample path that terminates in an absorbing state. Now, the key assumption of these Monte Carlo simulations is you're watching this trajectory and it hits an absorbing state. Now, you can take one of two assumptions. One is that you might not know the matrix, but you do know the set of absorbing states. That may or may not be true. The other is you watch the trajectory, it hits some state and it is in that state for a reasonable amount of time. Then you sort of declare that this is an absorbing state. Second one is a bit more dangerous because just because a Markov process is remaining in one state for a successive time instant, you cannot ever say with 100% guarantee that this is an absorbing state, right? I mean, if a Markov process has a self loop with non-zero probability, in principle, it can remain in the state for a very arbitrarily long time. So leave aside those issues. You presume that you have a mechanism for determining when the state has hit an absorbing, when the process has hit an absorbing state, and then you can restart the process at an arbitrary initial state of your choice. Then what happens is you keep going again and wait till it hits an absorbing state again. That is called a second episode. So remember that this is the formula for the discounted future reward, and the convention, I say it on a later slide, I should have actually said it here. The convention is that if you have a Markov process with an absorbing state, the reward is zero for the absorbing state. Meaning if you just stay there forever, you don't gain anything. So you might as well start again. Okay, that's the idea. So even though you have written summation from 0 to infinity, you can chop it off at a finite amount of time when it has hit the absorbing state. And then this assumption that you can restart at an arbitrary state means that your infinite sum basically is a whole bunch of episodic sums. But you don't put the gamma. I mean, what I mean to say is you start some initial state and you discount future rewards by gamma. You hit a reward, you hit an absorbing state, you restart the process, but then time starts then. So you don't discount immediately. No, that means if you think about the process runs for 100 time steps, so you have gamma, gamma squared to gamma to the 100. When you restart the process, you don't discount by gamma to the power of 101 because that's all gone. Now it is time 1. That's what I'm trying to say. So basically what you could do is to use all these partial sum to calculate the overall discounted reward. Okay? And this is what I'm saying, that because the reward is 0, if x is an absorbing state, you just only need to go until the time you hit the absorbing state, right? And then that gives you an estimate, and then you average over episodes. That's roughly Monte Carlo simulation methods, right? Now, one of the problems that you're going to face when you do Monte Carlo estimations is that, remember, you're trying to estimate the value v of xi for one particular initial state xi, which is not absorbing. Because if x is an absorbing state, by definition, the reward is 0. There's nothing for you to estimate. So now suppose there's one state of interest to you, and you watch the trajectory. The trajectory could go through x by more than once before it finally hits the absorbing state. So how do you handle that? There are two common methods that people are using. One is called first time estimate. The other is called every time estimate. And I had some illustrations of that. I commented them out because I thought the talk was getting too long, but I think that might have been a mistake. But anyway, it's fairly straightforward, the difference between the first time and every time estimate. Basically, all you do is that if it the trajectory passes through x of I, okay, you take the trailing sum, and if it hits x of I again, you add it one more time, and so forth. If you do that, that's an every time estimate. If you only do it the first time the trajectory goes to x of I, that's called the first time estimate. So what's the difference between the two? So in a Markov process with absorbing state, each sample path that terminates in an absorbing state is statistically independent of every other such path. This is a very useful property of Markov processes. It's not taught very often, but so think about a Markov process, it hits a loop. Then you restart it in some other state, and it hits the loop, it hits the absorbing state again. What is the relationship between the second path and the first path? And the answer is there isn't any. They're statistically independent. So, if you take a series of these episodes, you can think about them as statistically independent estimates of the value, the discounted value. So you can just simply average them. And there are inequalities like Hufting's inequality that tell you how close your estimate is to the true value. That's the good news. Some more good news is that if you use only first time estimates, they're all unbiased estimates of the unknown value V. Okay? And they converge to the true value as the number of episodes approaches infinity. Every time estimates are biased but consistent estimates. What does it mean? It means that if you look at what happens after a finite number of episodes, then the answer you get is not necessarily an unbiased estimate. Its expected value could be biased. However, as the number of episodes gets larger and larger, the bias goes to zero. So whether you use first time estimates or every time estimate, the estimate will converge to the right answer. So why would you use a every time estimate, which is a biased estimator? You just have more estimate. You think about a trajectory. So let's say the trajectory is 100 time steps long, and it goes through the state of your interest 3 times. If you use only first time estimate, you have only 1 sample. If you use every time estimate, you have 3 samples. So that's the reason for using the every time estimate. Okay? Is there a what, sorry?
Is there a recommendation on which one to use?
No, I mean, there is some result that in general, and this is not a theorem, this is just an observation. In general, every time estimates have greater variance than first time estimate. But because you have more samples, the estimate is closer to the true value. So lower mean, higher variance. So it's your choice where you want to be. Okay? Now, what is the shortcoming of the Monte Carlo method? Well, first thing is that the number of samples is just the number of episodes, not the total length of the sample path. So in other words, it really hits the absorbing state. You have got only 1 sample for V hat. Okay? And depending on the Markov process, the estimated number of times it hits an absorbing state can be much, much smaller than the total duration of the sample path. So basically, these require a huge number of observations. So let me just remind you in case you haven't got the point. This is all for the case where the underlying unknown Markov process has some absorbing states. So the mathematics is completely different from all the stuff we have been talking about until now, where I said the A matrix is unknown but it is irreducible. By definition, there are no absorbing states in an irreducible process, right? So processes with absorbing states also occur in learning problems, but mathematically they're more messy. And because the estimates are based on a long sample path, the variance in the estimates is very high, and partial episodes are of no use. So in other words, if you observe a sample path, after 1,000 times, it hits the absorbing state once, then you watch it 500 more times, it still hasn't hit the absorbing state. Then the last 500 are of no use, you just throw them away. Okay, that's what I mean by saying partial episodes are of no value. Now, I'm going to finish with a couple of ideas. Again, for these topics, the book by Sutton and Bartow is very clear, and I'm trying to condense everything into just 15, 20 minutes. And this is something known as importance sampling. I'll try to motivate that. So you can also use Monte Carlo method to estimate the action value function instead of the value function. And this is based on the episodes where every pair xi uk is visited. So if the underlying matrix is primitive, now change assumptions again. Way back when irreducible A, most recently a matrix with absorbing state. Now I've said this is not just irreducible, it is what is called a primitive matrix, which means some power of A is positive. Okay. Now look at the bottom bullet. If the policy is deterministic, it is impossible for every state action pair to be visited infinitely often. Do you see that? Every state may be visited infinitely often, but once you fix the state, the action is fixed. So if you want every state action pair to be visited, you cannot use deterministic policies. You have to use probabilistic policy. Okay? So for a deterministic thing, not every state action pair is visited, you use the probabilistic policy. So how do you generate this choice of probabilistic policy? This is the interesting concept called the target policy and the behavior policy, on policy and off policy estimation. And these are all words that people use without necessarily defining them very precisely. And the idea is the following. Suppose you want to calculate, remember that the discounted value is the expected value with respect to one probability distribution. But in that probability distribution, some states may be occurring not very often or very rarely. So you have to watch for a long, long time before those states show up. So instead you generate the samples according to a different probability distribution, which kind of evens things out. But when you do that, obviously the estimate you get is also off, because the probability distribution you're using is not the correct one. So essentially this whole business of importance sampling is to show that there is a way in which you can very simply correct for this mismatch, okay? And what did I do? I think while I was talking, the slideshow went somewhere else. Yeah, so I compressed several pages of detailed calculation to say, if you really want to calculate according to a particular policy pi, but you find it easier to simulate a different policy phi, so this is called the target policy, what you really want to evaluate, and this is called the behavior policy. Then there's a simple formula for doing these corrections, And that's really all I want to say without getting too much into details. Okay. And then the very last thing is called the greedy policy optimization. So you have a given policy pi, and you have not the true state action function q pi, but only an estimate for it. Okay? This is the problem. All the things I've told you till now don't give you q exactly. They only give you an estimate. So suppose I use this approximate q of pi to choose what you think is the best action. How close is it really? Right? So that is what this greedy policy is all about. If you choose the next policy to improve q of pi for each state action pair, this is called the greedy policy optimization. This is called the policy improvement theorem. And what it tells you is that if you do it this way, then the next policy you choose is always better than the previous policy. Okay. But assuming that this is the true V and not an approximate V. Okay. And if there is a state such that this inequality holds with strict inequality for a particular x, then this also holds with strict inequality. So anyway, I think I'll skip the last two slides because they're matters of detail. But what this says is, you start with an initial policy and corresponding action value function q, and then you choose the optimal policy by choosing the optimal action for each state using this q. Then you can keep repeating this choice of policies, and eventually you come up to the solution. This is called the pure greedy policy. Okay. And I think I'll skip these last three slides. This is just about what are called the epsilon greedy policies and so forth. I think I'll actually stop at 1, 2, 3. So that's all. So I'm just a little bit behind time, but not too bad, I hope. So yeah, let me just summarize by saying I knew even before I started the lecture that lecture 1 would be easy, lecture 2 would be moderately difficult, and lecture 3 would be like a snow job. So I tried to navigate you through the landscape of the third lecture especially. I would like to suggest strongly that you read the key references. The one on critical algorithms, as I said, you have two experts here in IISc. And the book by Sutton and Bartow is a very, very good source for Monte Carlo simulation and all for this greedy optimization methods. So my role, as I was told, was not to present any original material, but just to give you people enough of a background that you can appreciate the technical talks that are going to follow over the next 3 days. I hope I have done that. And if you have any questions, please feel free to ask. Oh.
Take some questions.
Oh, I think we have to be here for the photograph. I have to turn this on, I
If there are
think.
any questions, please feel free to ask.
The divergence condition that used to prove the convergence of the algorithms, is it sufficient or necessary condition?
So intuitively, the way to think about it, so here summation of alpha t squared is finite, but summation of alpha t is infinite. So where do these come from intuitively? So you want your iterations to explore the whole space so they don't get stuck in the local minima. That's the divergence condition. It guarantees that you explore all possible parts of the state space. The summation of alpha t squared being finite guarantees that your stochastic process has finite variance. So that's roughly the division of labor between the two. Okay. And if you read my papers on convergence of stochastic approximation, you can also see that the summation of alpha t squared being finite guarantees that the iterations are bounded. They don't blow up. Okay, they don't blow up, but where do they go? So the divergence condition, summation of alpha t equals infinity, guarantees that they converge to the right answer instead of just going round and round. So the stochastic approximation part I did not at all talk about in this lecture, but do invest a bit of time to familiarize yourself with that. Those are the first modules of my course, which I didn't cover here at all. Okay, I guess that's all. Right.
One more question. Does MDP or POMDP is the only one centric model for these all RL reinforcement?
No. There are as many models of RL as there are people. I would say that these are the most popular models. Let me put it that way.
Is there any other model like that?
I don't study any of them. These are the only ones that I study.
Alright, so let's thank again Professor Vidyasagar.
Thank you.
Here is a small token of appreciation.
Oh, okay. Thanks. I think we're supposed to pause.
Okay.
Thank you. What is this book?
I think one is against us.
Oh, whoa.
This, I think.
Oh, sorry. Thank you. I hope the mug is not broken. Okay, thank you.